Yes, welcome. So today we are going to discuss the new topic embedded firmware design and development. So in the previous recorded video, so you people understood the different computation models used in embedded systems. Now today we will understand how the embedded software systems firmware is designed and developed. The embedded firmware is responsible for controlling the various peripherals of the embedded hardware. That means we say the embedded firmware is the controlling algorithm, and it is responsible for controlling the various peripherals which are found inside the embedded hardware. So it also generates the responses in accordance with the functional requirements mentioned in the requirements of the particular embedded product. And in other words, you can say an embedded firmware or the controlling algorithm is something like the master brain of any embedded systems. And this firmware is permanently stored inside the read-only memory. So the different kinds of memories which we have already understood. So ROM is also one type of memory, which is the permanent memory, and generally all firmwares are permanently held in the read-only memory, and it is not possible for the firmware to change. So that is the reason it's called as firmware. That means it is permanently written to the read-only memory, and you cannot make changes to that because the memory is only read. So now designing embedded firmware requires the following. So one thing, whenever you want to design a firmware for the embedded system, it's necessary for you to understand the particular embedded product hardware, like various component interfacing, memory map details, and how many ports are there, and the details of the ports. Now all these things you got to understand if you are interested in developing the embedded firmware. So without the knowledge of these things, it's not possible for you to develop the embedded firmware. And the second thing is you should know the configuration and the register details of various hardware chips. You should know how many registers are there, what is the capacity of the registers, how many flags are there. Now all these things are very important, and you should know about the interrupt architecture. Now when you know all these things, then you can easily develop the embedded firmware. In addition to this, you should also know some kind of programming language. So either the low level assembly language or the high level programming languages like C, C++, or Java. Now these are all the things which are necessary for anyone to build the firmware. Now embedded firmware development process starts with this conversion of from firmware requirements into the program model. So whenever you have the firmware requirement, it has to be converted into a program model. So and I showed you in the previous session, so the different kinds of computational models, so that can be used for designing the embedded software. So that is what you have to do first here. That is, whenever you have a firmware requirement, so you got to convert the firmware requirement into a program model, and then you can go for using the modeling skills like UML, that is unified modeling language, or flowchart based representation. So so this is what is required in order to start with the firmware development. Next is embedded firmware design approaches. Now, how many different approaches are there in order to develop the embedded system firmware? So the approaches that we use in order to develop the embedded system firmware is purely dependent on the complexity of the embedded system and also on the functions that are performed by the embedded system and the speed of the operation required. Now all this things are necessary, when you want to decide which approach of embedded design, you have to use. So one is the complexity you should know, and what functions it has to perform you should know, and in what speed it should operate you should know. When you know all these things, so then you can make the decision like which approach to be used for developing the firmware. So there are two basic approaches used for embedded firmware design. One is the conventional procedural based firmware design, so which is, you can also call it as sequential firmware design. So and there is another name for this also, it's called a Superloop model. So procedure based firmware designers, it goes using the sequential programming model, and the other one is embedded operating system based design, EOS, or just you can say it as embedded operating system. Now first we'll try to understand the first approach, Superloop based approach, or the conventional procedure based firmware design. So this approach is used for developing the applications, which are not very time critical, and where the response time is also not so important. So the embedded systems, so where the less critical embedded systems, or the embedded systems are the applications where that are not time critical and the response time is not so important. So such type of applications can be developed by using the Superloop based approach. And this Superloop based approach is very similar to this conventional procedure programming language, where the tasks are executed one after the other. And this is how the tasks are executed in the Superloop based approach. It's like this: the task that is listed at the top of the program code is executed first, and the task which are just following that top task will execute next, and this process goes on till all the tasks are executed. So in a multiple task based system, each task is executed in serial in this approach. That means one after the other. So when the first task that is taken up for execution finishes its execution, the next task will be taken for execution. So meanwhile, if the first task that is currently executing wants to perform some input output operation or sleep for some event to get completed, so it's not possible for executing the next task. The next task will be taken only when the previous task is fully complete. Now the firmware execution flow for this will be something like this. It's written. So first thing, configure the common parameters and perform initialization of various hardware components like memory, registers, all these things. So first, configuring the common parameters or initialization has to be done. Examples are not necessarily initializing only the variables, so you got to do some hardware initializations as well, such as memory and register. After that, you can in the Superloop based approach, the system will start executing from the first task and then goes to the second task and goes to the next task, like this, all the tasks in the sequence, and last it will go for executing the last task. And after performing the execution of the last task, it will jump back to the first task and follows the same. If you want to do that in a repeated fashion for infinite number of times. And then the order in which the tasks to be executed are fixed, and they are hard coded in the code itself. So in the loop based Superloop based approach, the order in which the tasks are to be executed are already predefined, and they are hard coded into the code itself. So also the operation in infinite loop based approaches, and we can visualize the operational sequence listed above in terms of a C program. But C is the sequential programming language, the procedure oriented programming language, and that is the language which best suits for writing the programs using the Superloop based approach. So here is an example. We have a void. So first we do the configurations, and then we do, when I say configuration, it involves preparing the minimum hardware that is required in order to run this program, and then initialization, where we go for doing the software initialization, that is initializing the variables that are declared. And in a while one, I have the many tasks, task 1 to task n, and each of these tasks are going to be executed serially one after the other. The moment the last task finishes its execution, again it just goes back and repeats from the first task, since we are defining it an infinite loop. So now since the Superloop based approach is running inside an infinite loop, so the only way to come out of this loop is either by using the hardware reset or interrupt assertion. So these are the only two mechanisms through which you can make any task which is running inside the infinite loop in a Superloop based approach to come out. So these are the only two ways. Now hardware reset, what it will do, it will bring the program execution again. Say the program is executing somewhere here in between. Now when you do the hardware reset, the program execution will start again from the first task. So that is what is hardware reset, and it can also be done by using the interrupt request. So what interrupt request will do is, when these tasks are getting executed one after the other, so if there is an interrupt, that interrupt will make will stop or suspend the execution of these tasks for time being temporarily, and then it will execute the corresponding interrupt service routine. After the interrupt service routine is executed, so the execution of the task will restart from the point where it got interrupted, or from the point where it got stopped. And Superloop done, one more important thing here is that the Superloop based designs, they don't require the operating system. Operating system is not necessary, since there is no need for scheduling of the tasks or assigning the priority to each task. So because every task, you have the task, and the tasks are defined, so they execute sequentially one after the other. So you don't require an additional scheduling mechanism here, or additional priority based mechanism is not necessary, because everything is sequential, it happens one after the other. So your program is self caring itself, so that the tasks are executing sequentially one after the other. So that is the reason we say for the Superloop based design approach, the operating system is not required. Operating system is required when the tasks needs to be scheduled in a different order for execution, and sometimes when the priorities needs to be assigned to the tasks. But this approach, since it is purely sequential, which happens one after the other, so we don't require an external operating system to monitor that. Now here the code for performing these tasks will reside in the code memory without any operating system image. So the program itself is residing inside the code memory, and it doesn't have any OS image. And so Superloop based design, where it is deployed in very low cost embedded products, and where the response time is not so important. Now example we have here, as an example we have taken reading and writing data from R2 a card using the card reader. So this again is sequential, everything happens sequentially, and it doesn't require any operating system. Now operations like first in the sequence is checking the presence of the card. Now once the presence of the card is detected, so next it will go for authenticating the operation, and then it will go for next reading and writing. Now all these things, it happens sequentially, and it is not possible for you to interchange the order of these tasks. They got to be executed in this order itself. Now hence we say this Superloop based design approach, it doesn't require any OS, and this is normally used for low cost embedded products where the response time is not very much important. Another example is an electronic video game which contains a keypad and a display unit. Now here again the person who is playing the video game, so will select the required game to be played by pressing the key from the keypad, and he'll also get the response on the display unit. And if sometimes user misses a key press, it won't create any critical issues, so rather it will be treated as a bug in the firmware. So that's all. Now Superloop based design is very simple and straightforward because it doesn't have any OS related overheads. So this is one advantage of Superloop based design: simple and straightforward and free from all the OS related overheads. Now the drawbacks are also there. Drawbacks of this approach, the main drawbacks are, say any part of the system fails. If some part of the system which is designed, or the firmware which is designed and developed using the Superloop based design approach, if any part fails, so it might affect the total system or the entire system. And if the program hangs up at some point of time while executing a task, it remains forever like that, because we don't have the operating system in order to manage and make the system come out of the hanging position. Now, so that is one important drawback. Other one is the lack of real timeliness. That is what we told. So these things, this approach is specially used in designing and developing the embedded system where the response time is not that critical. That is the reason this is the drawback: lack of real-time timeliness. And there are corrective measures also for this. These are the two major drawbacks what we told. So the corrective measures is something like using interrupts for external event requiring all real-time attention. And by using the interrupts, you can immediately draw the attention of the processor, and to some extent you can try to match the real timeliness. The second approach is embedded operating system OS based approach. And when I say the operating system based approach for designing and developing the embedded system, obviously it should contain an operating system, and the operating system, again, it can be a GPOS, general purpose operating system, or RTOS, real time operating system. And when I say general purpose operating system, so this is very similar to the conventional desktop PC's operating system. And these operating systems, say for example Windows, Unix, Linux, etc. for desktop PCs. And using this general purpose operating system, you can create and run the user applications on top of it. So many examples are there. So these are all the examples: Windows, Linux, Unix, many Mac operating system, Ubuntu operating system, etc. So these are all the operating system which will allow the user to develop an application, and run. Now, and these things, the general purpose operating systems can also be used in a majority of the embedded systems. Say, for example, personal digital assistances, point of sale terminals, and patient monitoring systems. And when I say OS based application, whether general purpose operating system, it requires the driver software, because for every hardware device that is present, there has to be a driver software, because that driver software is the one which is going to control the functioning of the entire hardware device. Now, the second approach is real-time operating system based design and development of the firmware. So it's this operating system is employed in the embedded product, which requires the real-time response, or which demands the real-time response. Since the embedded system demands the real-time response, so the RTOS here, the real-time embedded operating system kernel, is responsible for performing a preemptive multitasking. What is preemptive multitasking? Say preemptive is forcibly taking. Preemptive meaning is forcibly taking back. If the CPU is currently executing some process or some job, and if that job is taking too long to execute, and if other processes are waiting from the long time in order to get the CPU allocated, what the real-time operating system will do is it can forcibly take back the CPU from that process and allocate it to the next thing. That is what is preemptive multitasking. So there is something called as non-preemptive multitasking as well. And non-preemptive multitasking, once the CPU is allocated to some process, so OS cannot take it back until and unless that process voluntarily gives back the CPU to some other process. But luckily HRTOS is preemptive multitasking. That means the HRTOS has the right to take back the CPU from the current process and allocate it to the next highest priority process if there is a need. Okay, so that is what is RTOS. Next, now embedded firmware development languages. In the previous thing you understood the embedded operating system design approach, two things: general purpose operating system and real-time operating system. Now embedded firmware can be this thing: a target processor or a controller specific language, such as embedded firmware can be developed by using this assembly language or low level language. When I say assembly or low level language, it is called as a target processor or controller specific language, because any program which you write using assembly language, it runs only on that particular processor. The one assembly language written for one target processor cannot run on the another target processor. And the second thing is a target processor or controller independent language. So we say assembly language is dependent language, controller dependent or target processor dependent language, whereas C, C++, and Java, so they commonly known as high-level languages, and they are controller independent or target processor independent. That means the program written for one target processor can also run on the another target processor. Now the another approach for developing the firmware is another language which can be used for developing the firmware is the combination of both assembly and high-level languages. Now wherever you require, say for example I'm using high-level language for developing the firmware like C programming language, in between I can also go for adding or mixing the assembly language. And similarly, say I'm coding using the assembly level language, and in between I need to add some complicated functions using the C language, then it is possible. That is also possible. That is mixing of assembly in high level language or mixing of high level language in assembly. So both are possible. So these are the three different approaches. Now when I say assembly language, it is language specific, so that means it's dependent on a target processor or a controller. Now when I say C, C++, Java, they are independent languages, and it's not dependent on one target processor or controller. You develop a program for one target processor or one controller, the same program can be run on another target processor or controller. Now assembly language based development. Now what is an assembly language? Assembly language is human readable notation of machine language. It is basically machine language, so but it is written using the mnemonics which the human can easily read and understand. So and the processor always deals with the zeros and ones, and machine language is again a binary representation. So we write in assembly language, we write the code using the mnemonics, and when I assemble it, so it gets converted into the machine language, which is in the binary representation, and this is what any processor can understand. So assembly language and machine language are processor or control dependent. So that means as I already told, the program written, the assembly program written for one processor or one controller or one family will not run or work on the others. Now Assembly language programming is the task of writing the processor specific machine code, so in the mnemonic form, and then use an assembler which will translate this mnemonic form into the machine language. Now we have the example here. Now the general format of writing assembly language is something like this. You have something called as an opcode followed by operands. What is an opcode? Operational codes, what the processor will understand. And then an opcode will be followed by one or more operands. Now opcode tells, as I already told, the processor what to do, and the operands provide the data, the information required by the processor in order to do that particular task. So we have the example here, move a comma, so 30, immediate number 30. Now this mnemonic move a is a mnemonic which is moving the decimal value 30 to the accumulator register. This A is an accumulator register, so this immediate number 30 we are moving it into the accumulator register. The same instruction in machine language, it is something like this. So this is the machine language code for this particular mnemonic. Now this first half, what you are seeing here, this 8-bit sequence is the binary value, represents the opcode of move A, and this value is the binary representation of this 30, operand 30. So this is the for the mnemonic move A, and this is for the immediate value, that is 30. Okay, and this is what the processor will understand. And similarly we have mnemonic increment A, increment the content of accumulator register by 1, and for this increment A, the machine code is this. Now these are the things what this move A, so this is